Okay, so today we are going to return to the inhomogeneous Green's functions. And so what we're going to be doing today is inhomogeneous Green's functions, sorry, inhomogeneous equations and the Green's function. So what, so the idea is that we are going to return to this inhomogeneous, keep on saying inhomogeneous, I'm sorry. We are going to return to this infinite dimensional analog of now the inhomogeneous matrix equation. So you would remember that we did this earlier. So there was M of U equals to F. This was the matrix equation of the self-adjoint matrix M. So what we are going to do, we are going to move on to this infinite dimensional analog of this, where we are going to replace this with an equivalent Sturm Liouville self-adjoint differential operator L. And again, what we will do is we're going to choose a weight function when we are going to define this forcing term f of x. Okay. Now the functions phi of x and f of x can be expanded in terms of a set of complete eigenfunctions of L. So let's suppose that these, so we are going to suppose the following. So we're going to take y1 x, y2 x, and so on to form this complete set of eigenfunctions. And so that essentially means what is going to happen is that L of yn of x. So this essentially means that this is lambda n w x. Sorry, yn of x and yn ym is equal to delta mn. And now what we are going to do is we're going to expand phi of x as summation n goes to 1 to infinity phi n yn of x, f of x, similarly summation again n goes to 1 to infinity fn yn of x. Okay. As in the matrix case, we're going to assume that f of x is known. So since f of x is known, fn of x is also known. Fn of x, remember, was fn is yn of f, this with the weight factor w. While we want to obtain phi x, that is, we want to obtain phi n of x. Okay. So good. So again, proceeding in the previous way, what we will do is L of phi is equal to summation n equal to 1 to infinity phi n L of yn is equal to omega n equal to 1 to infinity phi n lambda n yn, just by a way that we have defined things before. So this, by the equation that we started off with, is just w into f, which is nothing but, again, n equal to 1 to infinity fn, there's a w which sits outside, yn of x. Okay. So provided the eigenvalues are non-zero. So provided that the eigenvalues are non-zero, what we will have is 5p of x is summation over n equal to 1 to infinity fn by lambda n yn of x, right? So this is given by, this is what? This is summation n equal to 1 to infinity. Let's move this here. This is simply yn of f omega by lambda n into yn of x, right? So this we will write as n equal to 1 to infinity 1 over lambda n yn of x integral a to b yn star of t ft wt dt. This is which integral of a to b g of xt f of t dt. We will call this g. Where here in this last equation, what we have is we have that f of t is nothing but wt into f of t. This is the right hand side of the original inhomogeneous equation. And we have defined the Green's function. So Green's function, something that we have defined, this is gxt is summation n equal to 1 to infinity yn x y star n t divided by lambda. So Green's function is a function of two variables now, x and t, which so function of x and t, and this belongs in the domain AB cross AB. The important point is that the Green's function depends on the differential operator through its eigenfunctions, and more implicitly through the boundary conditions that you're going to impose. But as I'm trying to stress, this depends on just these things, and it does not depend, for example, on the forcing function. It does not depend on f. Okay. So since it does not depend on f, so if we know the Green's function, then we can solve it. We can use it to construct an arbitrary solution of the equation, L of y is equal to f for an arbitrary forcing term f, right? So in this sense, you can say that the Green's function is something that provides a formal inverse to a particular differential operator. So for example, so if you have L of f of y, L of x is equal to f of x, then in that case, what you'll get is y of x is equal to integral of a to b g of xt f of t dt. So this is how you solve for y. So this is sort of completely analogous to mu equal to f, where by you get u is equal to M inverse of F, right? So this is sort of, analogous to this. That's what the usefulness of the Green's function is, okay? So now that we have learned about the Green's function, what we are going to do is we're going to understand Green's function for some ODEs, right? So that's what we'll do. Okay, as we said, we now want to look at Green's functions for ODEs and consider now a general second order linear differential operator on the domain AB. And let's call this, let's call this L y of x is equal to alpha of x d2 dx squared plus beta of x d dx plus gamma of x. This is what the form of L is, acting on y is equal to some forcing function f of x, okay? So alpha, beta, and gamma are continuous functions in this particular domain, and we also require that alpha is non-zero. We will also require f of x to be bounded in AMP, okay? So the Green's function is of L of x is the unique solution to the problem. So let me define this. Green's function g of x xi is of L is the unique solution to L of g is equal to delta of x minus psi. And this satisfies the boundaries, satisfying boundary conditions. G of a xi is equal to g of b xi is equal to 0. Okay. You can immediately solve, for example, if you look at L of y of x is equal to f of x. So you can immediately solve this by saying y of x is equal to integral of a to b g of x xi f of xi d xi. So let's see how this actually goes about happening. This is very simple, but so L of y of x, just operate L on this particular solution, g of x psi f of psi d psi. This is integral a to b, L acting on g of psi f of psi d psi. This is just integral a to b delta x minus psi f of psi d psi. So this is f of x. So remember that this L, is something that depends. So this is a differential operator of only x. So L acts on G and does not act on F. So this is so that's good. We also know that the solution that we have constructed obeys y of a equal to y of b is equal to 0 as a direct consequence of these particular conditions on the Green's function. Okay, so that the solution obeys y of a equal to y of b equal to 0. This is just because our Green's function had the same boundary conditions. Very good. So now that we have learned that this is a formal way of trying to find solutions for any f of x, we now want to understand how to actually go about trying to get the Green's function, right? Constructing. So constructing. Okay, so this relies on the fact that whenever x is not equal to psi, L acting on this Green's function will be equal to 0. Okay. Thus, for both x greater than psi and x less than psi, we can express G in terms of the homogeneous equation, and we'll work with that. Okay. So let us suppose that y1 and y2 are the basis of linearly independent solutions. So basis of linearly independent solutions to the second order problem of L of y is equal to 0 on AB. Okay. Now we define this basis by requiring y1 of A is equal to y2 of B is equal to 0. Each of y1 and y2 obeys one homogeneous boundary condition. So on A side, the Green's function obeys L of G. Sorry, let me turn this thing around. Give me a sec. So L of G, so wire is getting in my way, is equal to 0, and G of A psi is equal to 0. Okay. This is for this one. But any homogeneous solution to L of y equal to 0, obeying y of A is equal to 0, must be proportional to y1 with a proportionality constant that is independent of x. Okay. So as we said, y1 and y2 are a basis of linearly independent solutions to this homogeneous problem. So this follows. So so let me write this down since this is important. Any homogeneous solution to L of y equal to 0, obeying y of A is equal to 0, must be proportional to y1 of x with a proportionality constant that is independent of x. Okay. So this means that G of x psi is equal to some A of psi into y1 of x for x which is in the domain which is in psi. Similarly, you can do it for the other thing. So this is going to be equal to some b of psi into y2 of x for the other domain, for x belonging to psi b, right? So a psi and b psi can depend on psi, but they have to be independent of x. Okay. So this construction gives a family of Green's functions for x in the range a to b, but you have to exclude the 0. Okay. This gives it in terms of a and b. And now we need to determine how to join these two for x equal to psi. Suppose g of xy is discontinuous at x equal to psi with a discontinuity modeled by a step function. Okay. So suppose g of x psi is discontinuous at x of psi, and we model this by a step function. So delta of x of g is proportional to so del x of g is proportional to the delta function, and del 2x is proportional to the derivative of this delta function, not 2, I'm sorry, primed of x by the psi. Now, L of g is equal to delta of x minus psi. So L of g does not contain any derivatives, but L of d does not no derivatives of delta functions. Right? If that is not the case, then what we see is that g of x, y has to be, continuous throughout a and b, and in particular, so contradiction, and hence g of x psi is continuous throughout AB, sorry, not XB, but AB, and in particular, at x equal to psi. Very good. So now let's integrate L of g is equal to this over a particular infinitesimal neighborhood around x equal to psi. Okay, so what is this? So psi minus epsilon to psi plus epsilon in of this guy. So del 2 g del x squared plus beta of x del g del x plus gamma of x g dx. This is now is equal to the integration of the delta function so this has to be equal to 1. So now let's examine this a little more carefully. Okay. So remember that g of xi is continuous, and alpha, beta, and gamma are bounded. Okay, so this final term out here cannot make any sort of a contribution if we make this integration region smaller and smaller and smaller. Okay, now let's look at the next term, right? G is continuous, and delta del x of G is also, del x of G is also bounded, right? So again, this term is something when you're going to make epsilon arbitrarily small, this can't again give you something non-zero. Okay, so this contribution goes up, and this also goes away. So what happens, what has to be happening is when you are looking at the limit of, so alpha is also okay, so let's just write this down. So limit of epsilon going to 0, integral of psi minus epsilon to psi plus epsilon, alpha x del 2g del x squared d of x. So remember that alpha is also, has been assumed to be continuous. So this is just alpha of psi. But now there can be a finite jump here. So del g del x at x equal to psi plus minus del g del x at x equal to, let me make this smaller. Going out of the writing region. Yeah, hopefully now. Yeah, so del g del x at x equal to psi minus. This is something that you get. And what is this? This is actually equal to 1, right? So to summarize, we must glue the Green's function, according to the following. So we must glue the Green's function according to number 1, g of x psi at x equal to psi minus is equal to g of x psi x equal to psi plus. So that's continuity. And number 2, del g del x at x equal to psi plus minus del g del x at x equal to psi minus is equal to 1 over alpha psi. So this is jump in derivative. Very good. So we have got these two now, and we are armed with this. So now that we are armed with this, so what we have, so let's in terms of this, let's just rephrase what we had before. So a of psi y1 of psi is equal to b of psi y2 of psi. So that's the first condition. And a of psi y1 primed of psi minus b of psi y2 primed of psi is equal to 1 over alpha of psi. Very good. So these are two linear equations for A and B. So for this, we can solve A and B, and A of psi is given by y2 of psi by alpha psi w of psi. We'll just define w, and B of psi is equal to y1 of psi divided by alpha of psi w of psi. W actually is defined as y1 y2 prime minus y2 y1 primed. This is also called the Wronskian. This is evaluated at x equal to psi. Okay, evaluated at x equal to psi. So to conclude, the solution, let's write this, the solution of L of G is equal to delta of x minus psi, obeying the boundary conditions. G of A psi is equal to G of B psi is equal to 0 is given by G of x psi is equal to y1x y2 psi divided by alpha psi w of psi and y2x y1 psi divided by alpha psi w of psi. So this is for A greater than equal to x greater than equal to psi, psi is less than x is equal to b. So g of x is going to be, so you can write this as a theta function as well. So g of x, y, you can write as a theta function. And then, this is 1 over alpha psi, w of psi, some theta function of psi minus x, y2, y1x, y2x, minus theta of x minus psi, y2x, y1x. This one's 1. So the solution to L of y is equal to f is then given by y is equal to y of x, if you wish, integral a to b g of x psi f of psi d psi, which is then given as y2 of x to integral a to x psi 1 x alpha x w of x psi, sorry, plus y1 x integral x to b y2 of x by alpha psi w of psi f of psi d psi. Okay, So that is what this is, and that's all good. So this one is, sorry, this one is yeah. So that is the solution to this formally. The integral that you have over xi is separated at x into two parts, which is x to a, and then there's a to x and x to b. So in the range in the range of a to x, we have xi less than x. So so this particular solution applies, and then what we have is so even though this expression incorporates the boundary condition at x equal to b, for the second piece, for this the integration of b to x, we have x greater than psi. So this one applies, that incorporates the boundary condition of at x equal to a. So this is a little, confusing to start off with, but hopefully this will be clear as we go ahead. And finally, I wanted to solve an example today to wrap this lecture up. So L of y is minus y double primed minus y is equal to f of x in the interval. So this in 0, 1, subject to, and the boundary conditions would be y0 equal to y1 equal to 0. Okay. So the general solution to the homogeneous equation is, of course, very simple. So solution to homogeneous equation is just y is equal to c1 sine of x plus c2 cos of x. Now we can take y1 equal to sine x and y2 equal to sine of 1 minus x. So then this so then our homogeneous so these are homogeneous solutions that satisfy the boundary condition at x equal to 0 and x equal to 1. So so then g of x psi is going to be given as a psi sine x, and here is going to be b psi sine of 1 minus x. So this 0 less than equal to x less than psi, and psi less than x less than equal to 1. Okay. So then what do we have to do? We have to impose continuity. So a sine psi is equal to b sine 1 minus psi. And we have to look at the jump. So that means b minus cos of 1 minus psi minus a cos of psi is equal to minus 1. Okay. Solving these for a and b gives the Green's function as the following. So this you can get the Green's function as x psi. I urge you to do this. This is 1 over sine 1 theta of sine minus x sine of 1 minus psi sine x plus theta of x minus psi sine of 1 minus x sine psi. So complete solution to the equation that we have here actually, with y equal to 0, y0 and y1 being equal to 0, is then given by the following equation. So y of x is equal to sine of 1 minus x by sine of 1 into 0 to x f of psi sine psi t psi plus sine of x by sine of 1 of x to 1 f of psi sine of 1 minus psi d psi. I can not fit my d psi in, so I'm going to move this. All right, so this is the solution now to this inhomogeneous differential equation, which we have just constructed from our Green's function. So hopefully that is clear, and we shall be going on to look at other things in a little while, and yeah, so hopefully that gives you a first flavor of what Green's functions are, and we shall resume our lectures in a short while. So that is it for me for now. So see you guys soon again. Bye-bye.